supply system is about from 50 to 100 years, so we need to be forward-looking. And estimation of water losses is often the most critical step. And you know, water losses are there, they are very relevant. In Italy, water supply system have an efficiency of about 65%, which means that 35% of the water that is taken at the source is lost. And this is quite a widespread situation. It's not because Italy is inefficient. Of course, Italy is difficult because it's mountainous, and therefore there are, you know, the water supply system works with high pressures, and when you have high pressures, you have more leakages. But on the other hand, it's very difficult to reach an efficiency that is above 80% everywhere. There are losses and leakages. Of course, this is not really lost water, because if you take the water from the river and then you have leakages from the pipes, the water goes back to the underground. It's not lost. But it's anyway, even if it goes back, this is a perturbation of the environment, because of course if you take twice from a river the water that you need, even if after the water goes back to the system, it goes back in a different place. So it's a perturbation of the original configuration. And the original natural configuration usually is a configuration that was dictated by an overall equilibrium. So the perturbation of this overall equilibrium, of course, is something that we want to avoid, even if it's not close to water. And also the estimation of other source or sink terms is very difficult. And for instance, you may consider water reuse, but it's not so easy to make a prediction. For instance, now it's more and more diffused, the practice of reusing water from wastewater treatments for irrigation. And this is fine, but of course this is something that is difficult to quantify because it requires economic resources, and the estimation is not easy. Okay, so the basic tool, and here I am slowly moving back to a more quantitative assessment. I dedicated about 40 minutes to principles. Now I am slowly moving back to engineering. And this is something that you already know. The basic instrument, the basic tool for water resources management is the water balance, which is very trivial. The problem is to estimate the terms of the water balance. The water balance in itself is very trivial. The water balance requires, as you already know, the identification of a control volume, which may be a water supply system, a region, a watershed, whatever. Of course, given that I already postulated that the approach should be integrated, when it's possible, you should look at extended control volumes. So just looking at the water supply system may provide a very limited perspective. It's better to focus on the catchment or the city. Because if you just look at the water supply system, for instance, you don't look at the possibility of reusing water. You just look at the water supply system, you estimate the demands, and you bring enough water to the system to satisfy the demands. But maybe that if you focus on the city, you see that there is a wastewater treatment plant, and you can use some water from the wastewater treatment plant for irrigation, for instance. So it's better to adopt a large control volume, but of course there are problems, because if you enlarge the control volume, you increase the complexity of the system, and you may increase uncertainty. And if you increase uncertainty, it's not a good thing. So this is your option. You are the engineer and you have to decide. You have to be aware that it's better to look at the large scale, but you have also to be aware that large scale means increased complexity. Increased complexity means increased uncertainty. And if you realize that the increase in uncertainty is not worth enlarging the scale, then you still focus on the local scale. And let me make an example by going back to the example of the wastewater treatment plant. So if you enlarge the scale, you may see that there is a wastewater treatment plant, and you may want to consider the opportunity of reusing water from the plant. On the other hand, you may find some uncertainties, like the water is not ready to be used, you need an additional treatment. The additional treatment, you are not sure if it can be done within a reasonable time. So some people may tell you it will be ready in 10 years, some other people may tell you it will be ready in 2 years. So there is uncertainty. Then you have to evaluate uncertainty and evaluate if you can take the risk or not. If you can't take the risk, or if you see that the uncertainty is really huge, like some people may say, who knows, maybe that we can't use the water, reuse the water forever, then you may say, okay, the uncertainty is too relevant, I prefer just to stick on the small system. So these are the two opposite issues that you have to always consider: the opportunity to widen the scale and the opportunity to reduce uncertainty. And then you as engineer take the decision. You already know, we already commented on this itemized list, estimation of water availability, water quality. Water quality is directly related to the example that I just gave to you. Or water demands, water losses, water source or sink terms, and the control volume. We already discussed about it. And then these are some side issues, very important: groundwater dynamics, groundwater withdrawals, irrigation efficiency, another very relevant issue. Because, you know, it's easy to quantify. I made an example at the beginning of the subject. It's easy to quantify the water demand for a plant, but then the question is, how much water should I take from the river or from my water source to make sure that the required water reaches the plant? There is in between the irrigation efficiency. And climate change, of course. This is a big issue, because people, when they want to question your decision, they say, what about climate change? And then you get trapped in a cul-de-sac, as they say in France, because, you know, climate change is something that is difficult to quantify. And we go back to the issue of stationarity. So people basically say, what about stationarity or stationarity? And then we have to be able to prove that we know the problem, and we know that in absence of any final quantification of no stationarity, we should use the stationary approach, because I told you my viewpoint. But there are people who are convinced that it's better to stay on the safe side, to focus on no stationarity, but then becomes a problem. Okay, so the water balance, how to compute it? First of all, the level of detail. So what is the level of detail? The time step. When you compute the water demands, in this case the time step was, for instance, day. But is the day the correct time step at which to compute the water balance or not? Should we focus on hourly demands or weekly demands? So what is the level of detail? Which basically means spatial and temporal scale of representation. So, for instance, when I estimate the water demands, what do I mean with spatial scale? Should I focus on the city as a whole, or should I look at each single house to look how many people live within each house, How many of them are young people who don't use water during the day? How many are elder people who use water during the day? So what is the level of detail? And the level of detail should be available, should be compatible with available information. It's useless to say that I have to focus on any single house if I don't have any means to get this information. How many people and who are living in any single house. So basically the level of detail is to be decided by focusing on the information that you have and by focusing on the purpose of the analysis. So as an engineer, you have to acquire a very strong practical sense of practice, let's say. So you have to really understand what is your problem in practical terms and find the most appropriate solution in practical terms. So basically, if I am estimating water needs for irrigation, in many cases it's useless to go to a very fine time scale. The daily time scale is fine, because irrigation is something that doesn't change at each minute. Usually when you deliver the water to the farmer, you open the pipe or the channel and you can keep the channel open for several hours. So there is no change at fine time scale. Instead, when you deliver water to people, you know, if you design at the daily time scale, then you take the risk of not being able to cover the peaks. So maybe that it's better to go at the hourly time scale. If you want in an empirical way, there are coefficients that you can use to estimate the peak use during a day, depending on the average use. So again, this is your decision, and you have to acquire a very solid sense of practice. This is extremely important for an engineer. And I am noticing, maybe I am wrong, because, you know, getting older, people become skeptical on the future. But anyway, let me say that sometimes I have the feeling that the sense of practice, we are losing a bit of sense of practice, of capability to look at very simple things and understand what is the very practical solution. Sometimes we make very sophisticated computations for identifying solutions that will be identified very quickly just by perception. And you have to try to keep this capability. And in order to keep this capability, you have to look at the everyday practice and ask yourself questions. Why this person is doing so? Why today, after a small rain, this street got flooded? There must be a reason. So when you see these situations, like for instance, let me take an example. On Friday there was a very heavy rainfall over the region. And this, my first question was, did we get some problems or not? And I'm still asking, because I didn't realize. I was away during the weekend, so I didn't realize. But in any case, if you see a very heavy rainfall and you don't see any problem, this is a question that you should try to elaborate on. Or if you see problems, same thing. So just try to wander and find solutions for everything that is related to water, if you want to become a water expert. Or sometimes you see strange things like downstream a dam, there is a river that is dry. So why is that? Because the river shouldn't be dry. There is the environmental flow that people need to release. So the solution could be the environmental flow is released, but it's infiltrates. So it's you can see it, but it's there. It's just underground. Another solution could be people don't release it and there is no control. Another solution could be that they release it, but downstream there is somebody taking the water without any permission to do that. So, you know, just try to figure out what's going on. I always say that an expert on water should ask questions to himself for any any fact that he noticed related to water. Okay, I think these issues here are, we don't need to discuss on them. And then there is the management phase. And pay attention because this is an important slide. So basically, what I said so far is you have to get information and you have to solve the water balance. But then you have to identify decisions. And to identify decisions, you have, first of all, to gain a perfect picture of the alternatives. So you have a problem. You identified the tool that you can use to solve the problem, the water balance. You identify the detail, the spatial scale, the time scale, but then you need to identify the solutions. Because of course, the way in which you apply the water balance depends on the solution. So you have to figure out at the beginning what are the alternatives. So if you have two users, you can see basically three alternatives. No water to user A, all the water to user B, the compromise, and no water to user B, all the water to user A. This is a very rough analysis. What I mean to say is that you have to identify any possible doable solution. And this is the third point that I listed here, evaluation of the possible alternatives. Once that you identify the possible alternatives, you need to identify a decision criteria by keeping into account that the decision must be transparent, so the decision criteria should be explained to the stakeholders. So how do you decide? By maximizing the economical benefit, by maximizing or by minimizing the water consumption, by maximizing the amount of water that is given to irrigation. So by giving priority to irrigation or giving priority to the civil use, keep into account that the European laws and therefore the Italian laws assign priority to the civil use. The civil use has the priority. But this is a decision criteria, a constraint. So make sure that you satisfy the civil uses, and then for the remaining uses you can take a decision. I'm making an attempt to change it, just give me 1 second. This is more, this is not good. This is worse. Because I wanted to change, because I have problems to see the screen on my PC, but I don't think that I can improve much. Okay, just let me see. Okay, I'm almost finished with the slides, so just be patient on this one. And even if you don't see here, I think I can get it. So basically, let me spend a few words on the strategies. This is visible. you have a first important option to evaluate, which is related to the strategy that you can follow to solve the problem of the water shortage. And you see two alternatives: mobilizing more water and water savings. And this is an important alternative. Mobilizing more water means that instead of concentrating on efficiency of water management, you try to take more water to increase your water resources availability. And for instance, this is frequently done when you build a reservoir, an artificial reservoir. So you need water, and the solution that you choose is to build an artificial reservoir which is big enough to compensate for your needs and the losses. And therefore you don't need to focus much on water savings, because the reservoir is giving to you plenty of water. Another option is to avoid the construction of the reservoir by maximizing water savings and, in general, efficiency of water uses. So let me make a couple of comments which are displayed in the last bulleted item. The first solution, mobilizing more water, was extensively applied in the past, because in many instances it's cheaper. It's cheaper to build a dam rather than optimizing the management of water supply systems in some cases. Also because, you know, when you build a dam, you can recover part of the costs by producing hydropower. So dams, some dams can be used for touristic purposes. So indeed, dams are an interesting opportunity. And in the past, this was the solution that was preferred. Also because there were plenty of opportunities for building relatively cheap dams with very good economical productivity. Then, by building a lot of dams, and you know, dams were built very extensively worldwide in all the developed countries, people realized after building the dams the problems that are related to the dams themselves. And one major problem is that the lifetime of a dam is between 50 and 200 years. You can't think of a dam lasting for 1,000 years. After about, you know, from 50 to 2,000 years, the dam is to be abandoned because it's not useful anymore, mainly because of siltation of the reservoir. Siltation is the process of filling the reservoir by sediment transport. And also, even if it doesn't get siltated, I think the past is siltated, yeah. And there is a loss of efficiency in the structure and also in the tools, in the contour of the dam, in all the equipments, and therefore, you know, the life expectation is quite limited. And of course, for us to think in the future for 200 years, it seems a very long time, indeed it's a very short time. The dam is not the final solution, basically. And also, we realized what are the environmental problems. So today, the most important rivers in the world are almost dried at their mouth because of the intensive water exploitation upstream. For instance, the Colorado River doesn't deliver any more flow to the Pacific Ocean. There was a discharge measuring station that was closed, I think, in 1970, because they couldn't measure any more water flowing. and also the Yellow River is dry for, I think, it dried up for the first time in 1972. It's a perennial river, but in 1972 it dried up in the lower part for the first time, and now it dries up for about 100 days every year, I think. So, and this is the case of the Yellow River, but any main river is intensively exploited. The Po River is an exception because it's just exploited in the mountainous part, but the lower reach is not exploited. The lower reach, there are no dams. This is just, it's an exception because for the Danube, for instance, there are dams in the whole course of the Danube, and also in the Danube there is a water shortage downstream. So basically we realized that there are several problems because, you know, building reservoirs also increases evaporation, and therefore, you know, it's not water lost in the strict sense, but for our purposes of water exploitation, water use, it's lost because of the increased evaporation. So basically today, given that there are several concerns and giving in view also of the increased power of green parties, we are trying to focus on water savings instead of increased water mobilization. There is the problem that if you focus on water savings, it's much more difficult to convince the population that your proposed solution is efficient. Because if you build a dam, it's a clear demonstration that you are doing something, and there is a lot of water that you can see. So people are very happy because they can see the water, the increased amount of water. If you just reduce water losses, people don't see it. So it's difficult, it's hard to believe for them that your proposed solution is a good solution, is a working solution. But anyway, you have to keep into account that today this is the priority. Water savings have the priority today. And also because, you know, water savings are much more sustainable because a solution for water savings has a lifetime that is potentially infinitely extended in the future. And also water savings are one of the so-called no-regret solutions. This is a term, no-regret solution, that in water resources management is gaining more and more popularity. No regret means that even if your solution doesn't work, you can revert your decision and take another solution without any regret or with few regrets. If you build a dam and you realize that you induce an environmental impact that was unexpected, you can't move back. You can't just remove the dam. The dam is there and that's it. And the environmental impact is there and that's it. Okay. I think that at this stage I can turn this off and move to the blackboard. Just 5 minutes and then I make a break. So at this stage we have identified the possible solutions, the possible alternatives, and then we have to take a decision. First of all, the decision is a fact. It's not something that you can treat mathematically. So we need to associate the decision, we need to find a solution to be able to treat the decision mathematically. And the solution is to associate the decision to a real variable. Like we did in statistics, we assigned an event, we associated an event to real variables, and then we introduced the random variable. Here we have to associate the decision to a real variable to define the decision variable. The most commonly used decision variable in water resources management is water allocation. And this is usually a real variable. Let's call it x1, y1, because water allocation can refer to several users. So there might be several decision variables if you have to deal with several allocations. So let's call it x1 because it refers to user 1. And this is a real variable, but we could find examples of binary variable. For instance, the decision could be build a dam or not to build a dam. This is a 0, 1, is a binary variable. In your problem, there might be more than one decision variable because, for instance, I already mentioned that you may deal with more than one user. And these decision variables could be a mix of real and binary variables. If you have more than one decision variable, then you can put them together in a vector. For instance, you can call the vector capital X, and the vector is given by x1, x2, x3. And if you have 3 users, and this vector is called decision plan. The problem is that usually you have constraints, because if you didn't have constraints, then there wouldn't be the problem. If the decision is just to decide how much water to give to 1, 2, and 3, and you don't have constraints, you just ask them how much water do you want, and you give them the water that they want. But in practice, we have constraints. So we have these constraints which you know are very important. So basically, at the beginning of your analysis, besides identifying all the information that you need, all the alternative solution, you have to identify the decision variables, the decision plans, which means identification of the alternative solutions, and the constraints. Let me make a very simple example. Let's suppose that you have 3 users and questions?
No, the decision plan
is a vector of decision variables and means identifying the alternative solutions. Because if the alternative solutions are done or not done, for instance, your decision variable is, as I said, a binary variable which is included in your decision plan. And let me make a very simple example, as I said. Let's suppose that your decision is just water allocation to 3 users, and the constraint, very simply, is x1 plus x2 plus x3 less or equal than an assigned amount of water Q. This is a very simple example, yet this is very, let's say that 95% of the water resources management problem can be reconduced to this very simple scheme. You have users which ask for water, and you have a constraint which is just given by limited water resources availability. But you may have some other more complicated constraints, like, for instance, let's suppose that one of the users is the river, the environmental flow, that you have to release downstream. Let's suppose that you take the water to give to 2 users from the river, and X1 is your environmental flow. The environmental flow is the minimum amount of water that by law you have to release downstream. In Italian it's called the flusso minimo vitale. So let's suppose that X1 is the environmental flow, and then you may have a law which says that X1 should be greater or equal than, let's say, Q star, which is the minimum environmental flow. So this is another constraint. You may have that these 3 uses should be, the sum of the 3 uses should be less or equal than the total amount of water, which you quantified in some way. And you may have a second constraint, which is that X1 should be higher than a minimum. So basically this is your preliminary analysis. You have to identify all the possible solutions, which means identifying your decision plans, possible decision plans, and then constraints. And then the question is, how do you decide? So let's suppose that, let's drop this one, because I don't want to make things complicated. Let's drop this. Let's focus on this case, and let me make it simpler by saying equal to. This is a second example. I changed it on the blackboard